Yeah, as mentioned, my presentation is about the prediction of PV power production in smart energy grids. And first, a small introduction about the topic. I don't think I have to explain to everyone why in detail we need smart energy grids in the system. I think we heard enough of that. But in terms of the machine learning part, recently, or like some years ago already, there's a growing interest in using machine learning-based methodologies for the prediction of energy forecasts in PV systems. It's really hard in smart energy grids to optimize the energy management between all the prosumers. And that's because we need a really precise or accurate prediction of energy supply and demand. But this is really difficult, first and foremost, in the production side because of the uncertainty, in our case, because of the PV installations. And secondly, from the, from the consumer side, it's difficult because of their constant change in behavior and so on. So I want to give you a small overview of the system we are building right now. So on the bottom left, you can see that we have multiple microgrids with batteries in there, and we connected edge devices to them to, for example, collect the data there locally and also make the predictions directly on the edge unit. Furthermore, we are collecting information about the battery states and so on, and they are getting directly transferred to the IoT platform of ours. There, we send it to the marketplace or the orchestra, which aggregates all the information we send for the different prosumers and also for the different microgrids. Those information, the aggregated one, are then sent back to the IoT platform for visualization. Afterwards, with those aggregated information about the battery, the production and consumption, we built an optimizer. And this one is planning the strategies for different, all the prosumers and also for the multiple microgrids. And it's getting executed, so we send those information like, do you want to trade with your neighbors and so on, which the optimizer did, directly to the microgrid. So if you should charge your battery, consume it locally, or send it between or within your microgrid, and also the pricing. This part we didn't figure it out that much yet, but that's why I'm here to maybe evaluate if some peer-to-peer options would be nice to implement there. My part is mainly on the bottom left. So as I said, we are using different edge devices for the prediction. In our case, we are having some Jetson nano units for the prediction. So now I will come to a methodology. In general, we have a data set of 5 years about the production, consumption, and also different weather features from January 2015 until December 2019. We retrieve it every 6 seconds, but for our use case, the paper I'm presented 2 weeks ago, we want to make a prediction for 1 hour ahead. So we average them down into 5-minute intervals. So we have a prediction of 1 hour ahead with 5-minute steps. They were collected in a Glava Energy Center in Sweden. It's directly in Arvika. In the next slide, I will show you exactly where it is. And in addition to those features, we also calculated the extraterrestrial radiation. This is basically the solar radiation outside of the Earth's atmosphere. And it's a fixed variable for a specific point and also for a specific time during the year. Furthermore, for the data set, we excluded the night times because they are not relevant. They don't give any more information about the production because during the night, PVs don't produce any energy. As I mentioned here on the left side, you can see exactly where the solar park is. So the red dot, it's really close to Karlstad, where I study. And here it's basically in the left side of Sweden. And on the right side, you can see the different weather features we collect. So we have the wind direction, precipitation, the typical weather features. In addition to that, we also have the produced power of the PV cells or the PV power production. As I mentioned 2 weeks ago, I presented a paper, and here I want to give you a small overview of one of my first steps as a researcher, like how can we improve the PV power production prediction. And we thought about a 3-step model where in the first case we are clustering the data. As I mentioned beforehand, we have multiple weather features, but here we want to try out for the clustering which combination of features give the best production in the best prediction in the end from the machine learning model. So we found a paper where they clustered only the solar irradiance, and we wanted to figure out if we increase the number of features, do we also get a better clustering? So for an comparison between this other paper and ours, we have the solar irradiance, then the historical weather data, which is basically all the features we have beforehand. And the third case is only the global and extraterrestrial radiation, because as you can see in the middle part, we have here, we have the different clustering methodologies. So we have the k-means Euclidean, the k-means with dynamic time warping, DTW, and then the last one, clustering with the clearness index. So the clearness index is basically the ratio between the global and the extraterrestrial radiation. That means, for example, we have the radiation directly from the sun, and then the one directly located at the ground surface. And with this ratio, we can estimate, okay, if are there any clouds, or how intense is the radiation at that point. And in the end, we have those 4 clusters. So we have the sunny cluster, so the day was mostly sunny, partly overcast, overcast, and rainy. Then for the second step, the model training, we used those specific clusters, for example, for a sunny day. We enrich it with the PV power production, the historical data, and we created 3 different kinds of machine learning models. In the first place, we used XGBoost, neural profit, and KNN. In the past, we also included LSTM and so on, but for this paper, we only used those 3. And yeah, in the third step, basically for the next day, we, in our case, for the day we observe, we identify to which cluster does it belong to. For example, it's a sunny day, so we are using the machine learning model of the sunny day, so that's the selection of the model. Afterwards, we generate the forecast and calculate the prediction error for our evaluation. So in general, we want to evaluate with this framework which clustering method performs best in our use case and in combination with which machine learning model. Here are some results. For example, for the partly overcast day, you can see that we have mostly a stable production, but sometimes there are drops within the production. So that means, for example, there's a cloud there or other circumstances. So you can see that the model performs really well with stable production, but then if there are those drops, it doesn't predict it really well. For the sunny days, for example, with a stable production, we can see that also the estimation or the prediction is really stable. We have the same phenomena as for the partly overcast days with the overcast days, that if there are really sudden drops in the production, the model doesn't predict it that well. But in the end, for rainy days, it has similar percentage error as the sunny days. So for the rainy days, we also have a really stable prediction in the end. The only problem childs, let's say, are the ones with sudden changes in the production. So yeah, for the conclusion, in general, it's really necessary to have an accurate prediction for the different management of the decision maker, so the decider in the system. But it's really difficult because of the uncertainty in smart energy grids. We evaluated different combinations of clustering and machine learning approaches for time series data to figure out the best combination. And in our case, it was the DTW k-means clustering, because it had like an overall, over all the 4 clusters, percentage error of 6.2%. And comparison with the clearness index, we only achieved a prediction percentage error of 10.77%. So in general, this is only like a small overview of what I did. It's from the most recent paper. But yeah, since the time frame doesn't allow me to talk more in detail about it, that's basically my presentation about it. Thank you.